this in-class activity that we did essentially in class, and you can kind of look at this and look at these problems. So let's look at the strain curve here. We're going to look at what is the stiffest material, toughest, strongest, highest yield strength, most ductile, most brittle. So the stiffest is going to have the largest Young's modulus. So we're looking for material with the largest Young's modulus. So that's the slope essentially of this linear region. So clearly the one with the highest slope is A. So A is going to be our stiffest. Toughest, let's go back to answer that last. Strongest. So what has the largest UTS? Well, this is the value of my UTS here for A, so that is going to be my strongest. What about the highest yield strength? Well, that's where, again, we deviate from linearity. So my yield strength is probably, let's say it's around here. So that's my yield strength, so that will also be A. What about my most ductile? So my most ductile, probably C or D. They both kind of, again, reach the same point. So most ductile, C or D. Most brittle, where does the material fail first? So here, so this would be my strain at failure. So this is my strain at failure here. So A is going to be your most brittle material. Now finally for toughness, so remember, toughness is essentially the area under the curve times the volume, right? So we're not given the volume in this problem, so we really can't make that assessment. So maybe you say C, maybe you say A, right? Maybe this area is larger than that area, but we need to kind of know what the volume is. So I'd say here probably A or C, for example, possibly. Multiple answers, we can't really answer that without knowing the volume. So let's get into the second problem. So we need to determine the angle and the values of the principal stress state and the maximum shear stress state for the 1, 2, 2, 3, and 1. So let's do this plane first. So for the 1, 2, I look at this. So I have minus 35. So this is 29. This would be my circle because, again, I have no shear. So I am already in my principal stress state. So that angle would be 0. So to get the maximum shear, that would be 45 degrees theta. And then my sigma 1 would be 29. My sigma 2 would be equal to minus 35. And then I know that my maximum shear value will just be 29 plus 29 plus 35 divided by 2, essentially the radius of that circle. So again, you can kind of calculate that on your own, or if you have questions, let me know. Let's look at the 1, 3 plane. So 29 minus 27, 0, 0, very similar. So again, we are in our principal stress state. So minus 27, 49. So we're in the principal stress state to get to the maximum shear. It's going to be 45-degree rotation. And again, we could find out, and again, the maximum shear value would be 29 plus 27, again, the radius of that circle. What about the harder one? This guy right here. So here, I have to draw my 2, 3 plane. So this is going to be, let's see, minus 35. Actually, let's first write down here. So my sigma 1 equals 29. My sigma 2 equals minus 27. So this will be minus 35. This will be minus, change here. Minus 27. This will be 45. This will be 45. So I'm going to have a point here, a point here, a point here, a point here. So if I want to kind of rotate here. So let's say I want to kind of find what's the angle to get to my principal stress state, because I'm not there yet. So I'm going to have to use Mathematica on this one, because I'm going to use my linear algebra approach. So my sigma, so my stress is going to be equal to my stress OG, so original coordinate system, is going to be minus 35, minus 27, and 27, and then 45. So that's that. Let me evaluate this here, here, here. So I need to figure out when do I get to my principal stress state. So I need to solve for T dot stress OG, and I want to figure out when does my shear, the third component, when does it equal 0 in terms of theta. So I'm going to do nsolve as well. So numerically solve it. So I'm going to get this value here because I know that the angle should be pretty small. And so my theta is 47.53. So I need to rotate counterclockwise, again, from this to get to that theta to get to my principal stress state. And I can figure out those values by simply doing the following. So I could just do this, /dot, theta goes to here, and then I will find those values. And this is basically 0. So this would be my sigma 1, this would be my sigma 2. So that's pretty much what we've got. Oh, I think I actually made a little bit. Actually, yeah, that's just, those would be the values that essentially I have here. So, yep, that is what we'll be working with essentially in this problem. So again, it's a wider circle than we might, ostensibly, anticipate here. So that would be my that stress, OG here. So that's that. So now let's go and let's figure out. So then the angle to get to my principal stress state. So that angle was about 47. Theta equals that. So the angle to get to here, we'd have to rotate basically clockwise 90 minus 2, whatever my theta was. So that's the rotation to get to the maximum, the principal stress state there. So that's pretty much it. So minus 35, minus 27, and then 45, and then these are kind of the values. So sigma 1, sigma 2 there. So I'm pretty sure that's all of the values. So you just kind of repeat that procedure, and then you'll be ready to, you can kind of solve all of these different values. So let's look at number 3. So arterioles are blood vessels, which branch from arteries to capillaries. They're 150 micrometers in diameter, 6 micrometers thick. The Young's modulus is this, Poisson's ratio. So E is 50 PA, Poisson's ratio is 0.4. We have these 2 strain gauges. They measure strain to be this in my strain gauge 1, and then we don't have it for 2. We need to figure out, okay, the pressure in these should not exceed 100 millimeters Hg. 1 millimeter Hg is 130 pascals. Is this true? So first off, we saw diameter. We saw that I need my current credentials, but we're going to ignore that for now. So whenever you see radius and thickness, so first off, what I'm going to do is I'm going to basically quit my kernel. So I'm going to quit my kernel because I don't want any crosstalk in terms of my variables. So my radius is going to be 75 times 10 to the minus 6. My thickness is going to be equal to 6 micrometers thick, so 6 times 10 to the minus 6. So that's my radius, 10 to the minus 6. So that's my radius, that's my thickness. So if R over T is greater than 10, greater than or equal to 10, then I am good to go in terms of essentially my value here to see a thin wall pressure vessel. So that is greater than or equal to 10. So once I know that R is greater than or equal to 10, I need to figure out, and I have a thin wall pressure vessel, and I'm going to kind of draw my coordinate system as follows. So this is going to be my 1 direction, this is going to be my 2 direction. So 1 is going to be my hoop. So my stress state is now sigma hoop, sigma L, everything else is 0, 0, 0, 0, 0. So, and then my strain is just going to be EH is equal to 1 over E, sigma H minus mu sigma L. And then my strain and longitudinal is going to be 1 over E times sigma L minus mu sigma H. So once we have that, and we also know that sigma H equals delta P R over T. So, and that sigma L is equal to delta P R over 2T. So once we have all these values, I know what E is. E is, Young's modulus is 50 times 10 to the 6 pascals. My Poisson's ratio nu is going to be 0.4. So what I don't know in this problem is delta P. And I also give them the information that that the strain in my strain gauge 1, which is my hoop strain, so my hoop is equal to 0.001. So now, with this equation here, I can solve for my delta P. So let's go ahead and bring this to the side. Let me bring this over here. So I'm going to scroll over here. So I know, solve, because I know that my E sub H is equal to 0.001. I know that those rest of those values here. So I'm going to solve that my E sub H, set that equal to 1 divided by Y times, and actually let me define. So sig H equals del P times R over T. My sig L equals sig H divided by 2. So we know those. So I'm going to do this, sig H minus nu times sig L. I'm going to solve for del P. So del P. And then, so my del P is 5,000 pascals because I've already covered everything, converted everything into pascals here. So 5,000 pascals. So let's see what our experiment was looking for. So high blood pressure was determined to be, it should not exceed 180, 80 times 133. So here we go here. So 180 times 133, because 1 milligram equals this. So yeah, we don't have high blood pressure, which is great for us. What's going to be the strain in my 2 direction, i.e. my longitudinal? Well, I know that E sub L is equal to 1 divided by Y, sig L minus nu times sig H. Nu times sig H should be smaller. And then slash dot del P. Del P goes to 5,000 because we figured that was the pressure in there. And as we see, it is smaller. So excellent. So that's pretty much it. So let's go ahead and let's get into problem 4 below right now. 4. So 4 says, look at the stress strain curve below. Look at the stress strain curves below. These stress strain curves are for new mystery proprietary material, cold rolled, and annealed at these different temperatures. Explain the trend in the yield strength. So what strengthening mechanism is employed? What's the scaling? Explain the trend observed in the yield stress versus annealing temperature at an atomistic level. What experiment has the largest concentration / density of defects? So let's go ahead and look at these values. So it appears, let's do a little bit of a ranking. So it looks like the yield stress of cold form is probably right here. Again, these are for cold rolled here, So for cold formed or cold forged, it's greater than the sigma yield for cold rolled, which is greater than sigma yield of basically 575, greater than sigma yield of 600, greater than sigma yield of 625. So this is the trend that we're observing here. So we know that when we anneal, two things happen, right? So let's pretend that we have some material, some defects, defects. If we put this in the oven or the furnace at long times, at high temperatures, these defects are going to kind of move and anneal out of the material, and you're going to end up with a material with much fewer, a lower, essentially defect density. So as we increase time, as we increase temperature, our dislocation density or a density of defects, density of dislocations or dislocation density decreases. And we know that for our cold rolled or our cold rolled strengthening mechanism, that our change in the yield strength is directly proportional to our dislocation density to the 1/2. So again, that's the strengthening mechanism being observed. So it's this, again, cold worked. Because again, when we cold formed or we cold roll material, we are increasing the number of dislocations in our material. And thus it becomes harder for those dislocations to move throughout your material. So we've got the strengthening mechanism. We've got the scaling. So let's cross it off. So we've got the strengthening mechanism. We've explained the trend. And again, we've actually already kind of talked about at the atomistic level. So annealing, again, we allow those dislocations to move out. When there's a lower amount of dislocations or lower dislocation density, these dislocations are free to kind of move around. Whereas here, they're impeding the motion of one another. So harder for dislocations to move amongst themselves. Because again, that positive kind of, you can treat it as kind of positive polarity, et cetera, et cetera, et cetera. Now, additionally, as we increase, the dislocation density decreases, but we're also, our grain size, so our DG increases. So the size of our grain increases as our time increases and as our temperature increases. So simultaneously, if we were thinking of this as like kind of grain size strengthening, it would have the same effect. As we anneal, we grow the grain size, we decrease essentially the yield stress of our material. So yeah, and then which experiment has the largest concentration density of defects? Well, according to the scaling, it must be the cold formed. So that's it. So that's number 4 in a nutshell. 5. Looking back at previous stress strain curves, what could be your explanation explaining the yield strength difference between CF and CR? So just for your information, this material can precipitate particle strengthen. These are the same alloy, however. So if the mechanism is precipitant strengthening, how will the critical radius for cutting volume change if the volume fraction increases? So one of the things that we could say, what's the difference between cold forming and cold rolling? So just for information, this material can precipitate particle strengthen. So one of the things that we can kind of consider is when we look at our yield stress for our precipitate particle strengthening, R, we have this R critical. So remember, we kind of look at it, curve like this. So on this side, remember, we cut. On this side, we bow. So here, maybe the cold forged is right here, but the cold rolled is either here or here. So that could be one potential solution to this problem. If the mechanism is precipitate strengthening, how the critical radius for cutting change the volume fraction of precipitates increases. So remember, if I have a system like this, lots of particles, so the volume fraction of precipitates or particles increases. So here versus this system here, remember, when I cut, the penalty in energy is going to be this creation of surface area. So if I'm cutting through more particles, like I'm creating more surfaces, right? If there's a higher volume fraction of particles. So what's going to happen is this critical radius is going to shift this way. Alternatively, if I have a system where it's like only one particle here, it'll shift the opposite way. So that's kind of how essentially it'll change And then let's see what else. Also draw how the yield stress will change as a function of grain size. Be sure to include the trend. So we know for our Hall Petch mechanism, so we know that basically we have the relationship for our grain size strengthening that our change in yield stress is going to be inversely proportional to our grain size. However, we know, so stress as a function of dg, this is true up until a certain point, about 10 nanometers, after which it starts to decrease again. And remember, that reason was because our grain size becomes so small at these super tiny, again, 10 nanometers is very, very small. There's only like one dislocation we could put in there. So we don't get the benefit or, kind of this phenomenon of dislocation pileup occurring inside of our grains. So that's essentially the phenomenon that's kind of going on there. So, yep. All right, let's move on to number 6. Material can also exhibit various creep mechanisms at different times and temperatures. The maps are all the same material. What can be happening? Explain the difference in the size of the regimes. Label all the deformation mechanisms. Blah, 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 blah. So let's get in here and let's look at this one here. So I'm going to zoom in a little bit. So if I zoom in here, I'm going to call a certain thing that's going to be happening. So TS is going to be my theoretical yield stress. Then I'm going to say dislocation glide is here, power law creep is here, will creep is here, and then Navarro-Herring is here, and then elastic E. So I know at low temperatures, low stresses, okay, this is my stress axis, I'm going to be elastic in here. So elastic, I also know this is my theoretical shear stress. This line, remember, is essentially where I yield at these different times of temperatures. So this is going to be dislocation glide. Oops, let me kind of go here. So this is TS, dislocation glide, TS, dislocation glide. And then now I have to kind of ask the question, okay, at high temperatures and relatively high stresses, where are my creep mechanisms going to dominate? Well, I know that this mechanism scales with sigma to the 4 to the 6 power. So at the largest stresses, that's going to be this first regime that occurs, it dominates at largest stresses. That's going to be this regime. So DLC, dislocation creep, and then DLC. Now, I also know that Navarro-Herring, this is bulk or lattice diffusion. So we're looking at diffusion within essentially the bulk material. So diffusion in here. So this is going to require very, very high temperatures because the activation energy of my bulk, my lattice, is very, very high. So this is going to dominate at high temperatures. So this must be H, again, regime that dominates at higher temperatures. And again, it dominates at higher temperatures here because, again, it's this kind of scaling here. We're looking at the bulk volume. We know that for Coble creep, we're looking at the essentially the activation energy in the grain boundary. So for Coble creep, we are looking at diffusion along these. So the activation energy of Q grain boundary is always lower. It's easier, faster to move through those grain boundaries. But the problem is, again, we don't have as many diffusive paths if we have a large, grain size. But as our grain size starts to shrink, so like this system, I have many more paths to kind of move through, right? So this is why it dominates at low grain sizes, because we also know that Coble creep scales to dg to -3, Navarro-Herring dg to -2. So we also know that that's occurring. So this must be Coble creep. And you can see here, the mechanism that must be going on has to be grain size strengthening. Why is that? Well, look at here. This has the lowest yield stress. And then also Coble creep is gone. So if my dg is really, really, really large, that means that my Coble creep region is very, very, very small. Again, because I don't have as many diffusive paths. And we also know that we have this relationship with dg to -1. So my grain size is huge. So this is the largest grain size. So if I label this as 1, 2, and 3, my dg1 is greater than my dg, let's look over here. This would be the next highest yield strength. Again, the Coble creep is a little bit larger here, but now it's huge here. So greater than GG of 2 is just greater than GG of 3. So that's how you would essentially basically go through and kind of guide and analyze these mechanism maps. So be sure to practice that. There's another practice problem in your problem set, and then that's pretty much it. So I hope this quick in-class activity has been kind of helpful and hopefully helped you in your problem set so you can do well on the exam. And then, yeah, I'll see you all next time. Thanks. And I'll see you in class in just a little bit.